Hello and welcome to my solutions for the mechanics mock. Okay, so let's have a look at this. Now we've got a velocity time graph question to start worth 9 marks. These can be tough. Yeah, don't underestimate the velocity time graph questions. They require a decent diagram, and that when you've got one car overtaking another car, or in this case a motorbike or whatever, they're normally quite tough then. So let's have a really careful go at this. Drawing the velocity time graph, though, or the speed time graph, should not be tough. Yeah, that should be pretty easy marks. But when you've got one thing taking over another, you need to equate the areas, and that tends to be a tougher question. Okay, right. So what have we got? We've got a car starting from rest. Yeah, so it's going to start with speed 0. It's a speed time graph, so let's put speed here. And it moves with constant acceleration for 30 seconds. Yeah, so actually, let's not draw it quite as steep as that. Let's draw it like this, because I think the other one goes faster than it, so I'm not going to draw it getting quite as much speed. Now, it reaches a speed of 15 meters per second. Now, if you read really carefully, it's a bit sneaky, this, but it then says very casually in just, what, 5 words, sorry, this speed is then maintained. So we've then got to draw it flatlining there, yeah? It's really easy to miss that first, I reckon, and that takes place at 30 seconds, doesn't it? Okay, so we've got that. Okay, so that is the car. I might even sort of color code that. That's the car. I could do the other one in a different color actually. Now let's see if this works out. When the car has been moving for 15 seconds, okay, so that's 15. A motorbike starts from rest at A and moves along the same road in the same direction as the car. And the motorbike accelerates 1.5 meters per second squared so that it catches up with the car. When the car has been moving for t seconds. Yeah. Now, I suppose the first thing you might ask yourself is that, is the motorbike going to be going like this, or is it going to be going like that? Yeah. Now I think, let me just quick, I've got the mark scheme open in the other window. I think they condoned either way of drawing it, so I don't think it would have made a difference to you. Yeah, if you'd have drawn it either way, you would have actually got the marks. Yeah. You can work out though whether which case it should be, that one or that one, just because we do actually know the acceleration of that, don't we? Because remember, on these graphs, acceleration is gradient, yeah, and gradient here is 15 divided by 30, so that acceleration is 0.5. You could just make a note of that, whereas this acceleration is 1.5, so it's going to be steeper. Now it's still possible for it to be steeper and going over here, but I think actually by the time you get to the end of the question, once you've worked out the speed, the top speed of the motorbike anyway, you'll see that it should be before here. But they would have condoned it either way, so it doesn't really matter how you draw this line, but you've just got to draw it so that at some point, and I suppose it certainly should be steeper. I mean, it is good to get it, I suppose, roughly right. So let's do, it's worth drawing these with a pencil. It really is. It doesn't hurt to kind of start again and just make things a little bit more accurate. Yeah. So I'm going to draw it like that. I'm going to rub out the 30 and the 15 and move them. It's just nice to get it to scale. It really is. It helps you identify errors if you've got it to scale. So that's 15 and 30, and then the speed's maintained. Yeah. And then with the red one, I think because this one's so much steeper, well, because it's 0.5 gradient and 1.5 gradient, we'll put it going over like that. And really, we don't need that bit at the end. We just need this time. There's a certain time, t, yeah, for both vehicles where the motorbike overtakes the car. Yeah, so that's like that. Cool. Okay, but like I say, if you draw your line like that, they would have condoned it. Key thing is the red one must have a steeper gradient than the black one, because it is a steeper gradient, because this has an acceleration of 0.5, whereas that has an acceleration of 1.5, and so it should be a steeper gradient. That's what they really cared about. Okay, and this is a time t, where, you always want to ask yourself when they give a time like capital T, is that since the car started? And I think it is. The motorbike accelerates 1.5 so that it catches up with the car when the car has been moving for t seconds. Yeah, there's lots of subtleties in that. But anyway, that's going to score you top marks for the first question. Now, this is going to be tricky, this bit, because it then just says find the speed of a motorbike at the instant it catches up with a car. Yeah. Now, there's no way we're going to be able to find the speed of a motorbike at the instant it catches up with a car unless we know this time here. Yeah. Oh, and by the way, let's put that on as 15 as well. So this is 0, this is 15, this is 30, and naturally this gap here is t minus 30. Always remember, and this is the other thing which students and myself sometimes get confused on in velocity time graphs. This t represents, how many seconds after 0. And so this gap's going to be t minus 30. And you always want to ask yourself, is this a gap or is this an actual value on the scale? Because people do get them muddled up. Okay, right. Now we need to work out the distances, yeah? So the car's distance, well, you can basically ignore this part of my diagram now because, it may well just keep pootling along after the motorbike's overtaken it, but we're interested in this distance. Now, what's the distance the car has travelled? Let's actually write it down. Tell the examiner what you're working out, or we will not give you marks for it, yeah? Because I don't know what it is. Actually label your equations. Okay, car distance. Well, what have we got here? We've got 30 times 15 over 2, yeah? And I know you like working it out like this. I'm not working it out as a trapezium. I'm just saying I've got that area, 30 times 15 over 2, plus, and then I've got this area, t minus 30 times 15. Yeah, let's actually simplify that. That's 225 plus 15t minus 100, what is that, 450? And so I make that 15t minus 225, I believe. Yeah, it's nice to get it all nicely simplified, yeah? Okay, right, that was the easier bit. Now, the motorbike. The motorbike is tougher because you don't know its maximum speed, or do you? Yeah? Can you write it down in some other way? Well, remember that gradient is acceleration here, yeah? And so if I want to find that rise, well, what I could do, let's just call it x at the moment. I could say x divided by run, which will be t minus 15, that has to equal 1.5, yeah? And so x actually equals 3 over 2, which is 1.5 times t minus 15. Okay, now I can do this. So the motorbike distance, and it's going to be in terms of t. And there's no chance you've got of getting this question right unless you've got a good diagram. I'm sure you notice that, yeah? You might as well, like certain questions you can do B and C even if you don't get A right, but this is not one of them. You need that diagram perfect. Okay, so the motorbike distance is going to be the area underneath. It's going to be this red right-angled triangle. And so we've got t minus 15, that's the base, multiplied by t minus 15 times 3 over 2, times by a half, yeah? Because it's a triangle. So base times height times a half. Okay, so now we can actually write that as 3/4 t minus 15 all squared. Okay, so what have we got here? We've got this distance, we've got this distance. We can equate the two and find t. And that's definitely most of the marks for this question. I'll tell you how many marks it is in 1 second. So we equate the distances, 3/4 t minus 15 squared. Really, this is quadratic, so we're going to have to times it out. I'm going to times the 4 over here, actually, giving me 60t minus 900 equals 3 times t squared minus 30t plus 225. Yeah, this might not be the quickest way. It's just a way which has occurred to me to do it right now. We don't always spot the quickest way of doing things, do we? Okay, so we get 60t minus 900 is 3t squared minus 90t plus 675, and so we get 0 equals 3t squared. That's going to be minus 150t, and then it's going to be plus 900 plus 675, which is 1575, I think. Okay, you could divide that all by 3, so you get 0 equals. You don't have to, actually, though. My calculator, which I've got here at the moment, is a really naff one, so it doesn't solve quadratics, but if you want to just go ahead and solve the quadratic here, be my guest. I'm just quickly simplifying things. 525. Okay, so 0 equals. Okay, now is this going to factorize? Let me just think. I think it does, actually, to t minus 35 and t. One second, let me just think in my head. T minus 15, I think. Yeah, it should be t minus 15. So t equals 35 or t equals 15. Now, you think about it, I should have spotted definitely the t minus 15 straight away there. What that's saying is at 15 seconds, like, you know, the motorbike distance is 0, and therefore, you know, and the car's distance is 0 as well. And so, yeah, like, yeah, sorry. Yeah, t equals 15, the car's distance is 0. Why would the car's distance be 0 there at 15? It doesn't look like 0 distance to me. Oh, from the motorbike, yeah. Because, yeah, the motorbike starts 15 seconds just at the same time as the car's moving, isn't it? Yeah. It starts from yeah, yeah. Cool. Okay, so, yeah, you get t equals 35 seconds. Okay, we can now easily work out the speed. The speed is just going to be, let's go back to our diagram. Speed's just going to be how much, basically this distance, 35 minus 15, which is 20, and we need to work out the speed, and we've got the acceleration, so we can use this equation here. We're just basically finding x here. So x equals 1.5 times by t minus 15, which is 20, and so that speed is 30 meters per second. Yeah, and we're just using the gradient once again for that. Okay, hopefully that makes sense. Like, yeah, it's an interesting question. It really is. I like those ones where the car overtakes the motorbike or the motorbike overtakes the car. They always make you think. They really do always make you think. There's no doubt about that. It's yeah, it's a toughie. It really is. Okay, right. Let's do the ships one. Oh, I don't know why I've got that annoying thing. That's kind of annoying. Let's see if I can suss out the question anyway. This one looks like quite a nice one. These used to be very common. Firstly, it's constant velocity. Yeah, constant velocity, as far as I'm concerned, as soon as I see that word in a vectors question, I think r equals r0 plus vt. Yeah, if it was constant acceleration, I'd think suvat. If it was variable acceleration, I'd think calculus. Yeah, and that's the rules basically for vectors questions in mechanics when you've got this movement stuff going on. Okay, what do we know here? Position vector of q relative to the origin is 612. That would be my r0 for q. And this is what we've got to do first. Yeah, so if I'm going to write down q's, general one, I don't know why I'm doing q first. Oh, I might need to take another picture of that actually, because I think that's giving me a vital part of the question. Let me just quickly look on my other screen, which I've got here, so I can actually find the question. Actually, I might have it on the downloads still. Let's have a look. Downloads. Oh, if you've ever looked at my screen online, you'll see that my computer has far too many icons, and that's what my downloads folder is like at the moment. Oh, mock papers. Let's try this one. Okay. No, that's GCSE, I think. This one. Apologies for this. I'll be with you in 1 second as soon as I find the question. Oh, I'll quickly just look it up on my... I feel like there's velocities under there. Oh no, hang on, is it down here? The ship P is moving with velocity 10J and the ship... Oh, right, okay. I think actually what's under header default page style is not important. Okay, so if I need to do this, I just need the R0, which is 612. Notice, yeah, I'm using column vectors. Who on earth would use I and J if given the choice? Not me. Position vector relative value is 612, and ship P is moving 10J and ship Q is minus 86. Yeah. That is what they're looking for when they say P and Q in terms of T. They're looking for the general equation. I'm just using R equals R0 plus VT. Initial position plus velocity times time. That's all it is. And so P, very similar. Does P start from the origin? That's what I'm missing, I think, underneath that little thing. Let me have a quick look. I've got it open on my other screen. So just give me 1 second to check this out. This is question 8. Okay, sorry, apologise for the delay here. Fast forward the video if you're bored of me talking till the point till I get to the juicy answer. Okay, here we go. Initially, P is at point origin, yeah. Right, okay. So this, if you like, is 0, 0. That says initially P is at point 0. Plus, and now its velocity is just 0, 10. Yeah. And this is why I don't like I and J, because it's not so clear that it's 0, 10 when you just say 10J. It's easy to make a mistake there. That's P and Q in terms of T. If you really want to write it down, if you're paranoid and you like writing down in I's and J's, okay, here goes. But honestly, it's not necessary. And then P is just 10JT. Yeah, there we go. Q and P in terms of T. Calculate the distance of Q from P when T equals 3. So just T equal 3 here. Where is Q? Yeah, Q is going to be at, and this is what I mean, I can't read that, but this I can just say T is 3, 6 minus 24 is minus 18, and then 12 plus 18 is 30. Done. Okay, right, where's P? Set T equal to 3, 0, 30. Yeah, find the distance between them. Well, as you can see, they've both got the same y coordinate here, so the distance is going to be 18. But if you really want to do the distance formula, Pythagoras, you're going to end up saying square root of minus 18, I suppose, if you like, squared, plus 0 squared, which is 18. 324 square rooted, which is 18. Hopefully that makes sense. That's a nice one. This question is nice. You've probably got this one right, I'm guessing. I'm hoping you've got this one right, because it's not a bad one at all, this one. This one looks really, really nice. Okay, part C. Calculate the value of T when Q is due north of P. Okay, so if an object is due north of another object in vector land, yeah, then they will have the same x coordinate. Yeah, it's as simple as that. Look at that. Two objects. One's due north of the other one. Look at that. They've got the same x coordinate because they'll lie on a line x equals. So we just want to make sure the x coordinates are the same. So I'm just going to say 6 minus 8t equals 0 plus 0t, which is, of course, 0. So I get 6 minus 8t is 0. So 6 equals 8t. So t is 3/4. Done. That's question 8. Not a bad one, that one. That one's the nicest one. Definitely nicer than the first one. The first one really made me think. Okay, right. Question 9. What have we got here? So we've got a plane, and we've got a dodgy diagram there. Is that supposed to be alpha? Tan alpha, yeah. Okay. Tan alpha is 5/12. Remember, do the prep work on these questions. Tan alpha is 5 over 12. That's opposite over adjacent. 5, 12, 13. Therefore, sine alpha is going to use Pythagoras to find a 13 if you're not sure about that. But that means sine alpha is going to be 5/13 and cos alpha is going to be 12/13. Yeah, do the prep work. Okay, we're going to add some forces to our diagram. I'm actually going to draw the diagram out again because I don't like things pushing into the object. I like consistency, and so I'm going to have all my arrows coming out of the object. So I'm just going to move that over there. A push is exactly the same as a pull. Like, you know, it's just happening from the opposite direction, but it's the same thing for all the forces. Okay, so let me just draw this again. Nice clear diagram. Alpha. I'm going to have 30 going along like that. That's alpha as well. I'm going to have R, which is always perpendicular. I'm going to have the weight, which is 20. I'm going to draw the little dotted lines on because that will be alpha. And I'm going to draw the little dotted lines on here. Now, if you're wondering how I draw these triangles, you always want it parallel and perpendicular to the slope. So the two sides of your right angled triangle are always going to be parallel and perpendicular to the slope. And what's more, the force will always be the hypotenuse on your triangle. The magnitude will always be, the force value will always be the hypotenuse of the triangle. Now, is this rough? Yep, it's rough. And is this moving up or down the slope? It's probably in equilibrium, actually. Okay, it's sliding up the plane, I think, looking at that. Let me just read this up here. A package of weight 20 is moving up an inclined plane. If it's moving up an inclined plane, friction must be going down the plane. That's the most difficult thing. And if it's moving, friction will be at maximum. Okay, so we've got the diagram drawn all right there. Now, what are we doing here? We're finding the magnitude of the normal reaction on P, and they're not really offering much for this. And that's because if we equate in that direction, yeah, perpendicular to the slope, we're going to have R equals 20 cos alpha plus 30 sine alpha. Yeah. Now we've already worked out that sine alpha is 5/13 and cos alpha is 12/13. So we can say r equals 20 times by 12/13. That's supposed to be a times, not an alpha. It looks like an alpha, doesn't it? 20 times 12/13 plus 30 times 5/13, and that equals, I'll just get my calculator out, 30 newtons. Is it exactly 30? I'm amazed at that. 30. Maybe I'm just it's too early in the morning. I have only had one coffee this morning, and I'm not happy about it. 12 divided by 13 plus 30 times 5 divided by 13. It's exactly 30. Clearly you can factorize this. I'm being really naive there. I almost want to know exactly why that's exactly 30. If I take out the 1/13th, I must be being an idiot. 20 times 12 plus 30 times 5. That must come to 39, I guess. Sorry, 390. Yeah, just the way it is. Okay, right, cool. So that equals 30. Sorry, I was just mildly interested there. Find a range of possible values of mu. Range of values of mu, yeah? And that's because it's normally because of like friction being at a maximum or not, yeah? And so you need, you need friction to be less than or equal to something, yeah? It's because F max is going to be equal to mu r here, yeah? Okay, right, let's use that fact, yeah? Okay, so we're going to have to go up and down the slope now, and we always do that. We're going to have to go the other way. Okay, so we've got 30 cos alpha this time, going up the slope. Well, that's going to equal F max plus 20 sine alpha. Force is going down the slope. And so we've got 30 times cos alpha was 12/13 minus 20 times 5/13, and that equals F max. That's given me an F max value of, let me just quickly work it out, 20. So F max equals 20 newtons, and therefore mu is a third. Yeah, because mu is going to be F max over R, which equals 20/30, which is a third, 2/3, sorry. Now, why are they saying range of possible values of mu? Well, because provided, remember, the bigger mu is, the rougher the surface is, yeah? And so provided mu is less than or equal to 2/3, we're going to have motion up the slope. Otherwise, we wouldn't have had this balance. We've assumed here that it's in limiting equilibrium, yeah? We've assumed that the force is balanced there. Really, I suppose what I should have done throughout, and let's be strict here, is said, well, 30 cos alpha should be greater than or equal to F max plus 20 sine alpha. And that's because the forces, if it's accelerating up the slope, yeah, then the forces up the slope should be stronger than the forces down the slope. And that would give me this. Yeah, this is strictly speaking how you could do it, and it's perhaps a little bit more systematic, because I know some people get confused with the inequalities in mechanics. You should have that. Now, if F max is greater than or equal to 20 newtons, yeah, if this is going to be 20 newtons or bigger, well, that would make, let's actually write it down like this. R will still be exactly 30 newtons, if you see what I mean. Oh, sorry, I've got the sign wrong way around there in the last thing, haven't I? F max should be less than or equal to 20 newtons. Well, if that's going to be 20 or less, this is going to give you mu as, 2/3 or less, if you see what I mean. So you can just say then, as F max, as mu equals F max over R, you can just say hence mu is less than or equal to 2/3. Yeah, if you really wanted to do it properly, I'm sure they would have condoned you not doing it like that. I'm just looking in the mark scheme to check that they wouldn't have minded me doing like that. No, they don't mind you equating it at all. And so yeah, they just expected you at the end to recognize, well, if mu was less slippy, yeah, more slippy, sorry, and less rough, then you can just write down the answer. But that's technically the way you might want to do it. Okay, right. The horizontal, and the thing which made me realise it's an inequality, by the way, is the fact that it's a range of possible values of mu. Okay, the horizontal force is now removed and P continues to slide up the plane until P comes to instantaneous rest. This happens in a later on question as well, doesn't it? Package P then slides down the plane. Given that mu equals a third this time, find the acceleration of P as it slides down the plane. Okay, so draw the diagram out again. Yeah, it really is a case of draw the diagram out again. Friction's going to be going up the plane now. That's why we're drawing the diagram out again. Yeah, don't be lazy here. Draw it out again. The horizontal force is removed as well. So all we've got to do is find the friction down the slope. This is still alpha though, and this is still, the weight's still 20, I'm guessing. Okay, so what have we got here? We're going to have to say, well, firstly, R is 20 cos alpha. There's no other forces involved now. Yeah, that's great because we know cos alpha. I think cos alpha was 12/13. Yeah, there we go. So 240/13 because it's 20 times 12/13. Yeah. Okay, right. That's R. Okay, right. That's good. Because remember, F max is going to be mu R. So that's a third times by 240/13. So that's going to be 80/39. 80/13, sorry. Already accounted for that. Okay, that's F max. And so if I want to work out the acceleration, well, what you've got is stronger forces, which is 20 sine alpha, minus weaker forces, which is 80/13, that's your F max, equals your mass, which is, now, what is the mass of this object? Well, we know the weight, and the weight, that's slightly annoying, that, yeah? Because if you know the weight, well, weight is mg, isn't it? Yeah, as in like mass times 9.8 equals 20, and so mass is 20/9.8, 20/g. Yeah, that's annoying, that is. I'm not happy that they've got that in the question. I've only just noticed that. So you're going to have 20/g here. It's a sneaky one, times by the acceleration, and now we can find the acceleration just by plugging all this in. And I will be pretty keen to check my answer here because like I said, I haven't done any of these questions before. 5/13. Okay, sine alpha is 5/13 minus 80/13 equals 20g/g times A. And so A equals, let's have a look, 100/13 minus 80/13. Well, that's 20/13, isn't it? 20/13 divided by 20 divided by 9.8, roughly 2. Okay, I'm getting 0.75 to 2 sig fig, or 0.754 to 3 sig fig meters per second squared. Just check the answer on the other screen. Yeah, that's correct. Right. Okay, that's yeah, that's slightly annoying that they made you calculate the mass there at the end. Do you know what I mean? But mass is always just well, mass times gravitational pull is weight. Okay, the fun ones at last. I actually really like these now. I remember when they first came into the course, I was like, wow, I'd never seen them before because I'd never taught the old M2 before, which is where they came from. Incidentally, if you want to find more questions on this, look at the old M2 papers. But now I absolutely love them because they always work the same way, which is take moments and then uppies equal downies and then lefties equal righties every single time. Yeah. Okay, so let's quickly draw the diagram. The diagram, once again, is everything. Okay, we've got, I think, this going on. This is 2, this is 1, as in the whole thing's length 3. I prefer to do it like that. But we do have the weight of the uniform rod acting in the middle, and so that is 40 newtons going down there. That is 60 degrees. And I'm going to talk about some other forces. This is also pulling it up here. That's a tension, yeah? Okay, right. Those are the easier forces to put on there, and it's worth putting down that 2 is now suddenly misleading. Let's have it as 1.5 and 0.5 and 1. Can you see? Then I've clearly got the distances labelled. It just makes it a bit easier. Okay, right. Now, it's one of these ones where something's leaning against a wall. Now, you've actually got 2 forces here which together make up the contact force. You've got like what you consider as like a normal reaction, which is like pushing against the rod like that. And then you've got a friction as the thing scrapes down the wall like that, yeah? And between N and F here gives, if you combine those two forces and find the resultant force, you've got the contact force, yeah? Because both friction and normal reaction are contact forces. If you always draw it as X and Y or something like that, or V and H, vertical and horizontal, that will give you an idea. But really, this is like, I think of this as a frictional force, and this is a normal reaction. And when you combine the two, you get the contact force. Okay, right, so that's our diagram. Now, what do they want us to find first? The tension in the rope. Well, you know, if you're finding T here, doesn't it make sense to knock out F and N? And you knock it out by taking moments at A. Yeah. Also, get the moments equation done first, like if you can, or if it's necessary, just because that gets rid of these two. And then what we've got to do is we've got to figure out what this angle would be here. Yeah. Now, if that's 60, well, then that's 60 because there's a Z angle there. So that's 60. So this must be 30. Yeah. Okay. So taking moments at A, can you see that if you, I always tell people, advise people, think of this as like a pencil or something like that and hold it at A. If you push it in that direction, it will turn like that. Whereas you push it in that direction where the T is going, it will turn like that. So that's your clockwise moment. That's your anti-clockwise moment, and they should equal each other. And so what have we got here? We've got 1.5, always do the distance first because it's really easy to forget it, multiplied by 40 cos 30, yeah? That's the perpendicular component of the force that you've got to do it. Like you can do moments in two different ways. You can do force times perpendicular distance or distance times perpendicular component of the force, and that's the way I do it, distance times perpendicular component of the force. So you've got 40 cos 30, and that should equal 2 times, I'm doing the distance first, and this is just t because it's already at right angles, so the perpendicular component of the force is t. Now that's root 3 over 2, so if you times it by 40, you've got 20 root 3, times it by 3 over 2, you've got 30 root 3, divide it by 2, you've got 15 root 3 for your t, yeah? And that's the force. I think it comes to about 26 newtons. Okay, right. Magnitude of resultant force acting on the beam at A. Magnitude of resultant force. That means we need to find F and N and then combine them so we can find the magnitude of the resulting two forces at A. Okay, right. And you don't have to think of them as two separate forces. You can think of them as the same single contact force. But I think it's really helpful to think of the part of the contact force which is friction as it scrapes down, and the part of the contact force which is just like a push out because you're pushing into it. Okay, right. Let's do it then. So we've done our moments, so it must be now uppy downies and lefty righties time. Yeah, you never have to take moments more than once, or I've never really seen it happen, to be honest. Now to do this, I'm going to do straight up and straight down. You could resolve, in different directions, but let's just do this straight up and straight down. So that means that straight away, if that's 60, well, this would be 60, so this would be 30. Yeah. So make sure you're good with alternate and corresponding angles in these diagrams, because otherwise you're going to really struggle. Okay, ups, we've got a t cos 30 plus an f, and that should be equal to 40. Yeah, because that's going straight down. Lefty righties, oh, by the way, that gives us enough to find f because we know t. Lefty righties, might as well do it now. N equals t sine 30. That's it. T sine 30 is n. Yeah. So yeah, these questions get really nice after a while. If you do a few of them, you will get better. The problem is the Edexcel textbook is awful on this topic, as in they give you about 7 or 8 questions, not very many. I think it deserves its own chapter because it seems to be in the exam every year. I hope one year they actually set a flat moments question, because otherwise why am I teaching flat moments? But they never seem to at the moment, so there we go. But they will do one year, I'm certain of that. Okay, anyway, we've got 15 root 3 times by root 3 over 2 plus f equals 40. And so f is going to be 40 minus, what is that? 3 times 15, 45 over 2. And that, of course, comes to 35 over 2, I think. Okay, n is just half of t, and t is 15 root 3. So that'd be 15 root 3 over 2. Because sine 30 is a half. Okay, right, now the magnitude is therefore Pythagoras' theorem, square root of 35 over 2 squared plus 15 root 3 over 2 squared, square rooted, and what does that come to? Let's have a little tap on the calculator. Let's see, 15 root 3 squared divided by 4 plus 17.5 squared, I suppose is the quickest way to type that in, and root the answer. Okay, I'm making that 21.8 newtons, or 22 newtons, or the square root of 475. Let's make that 21.8 newtons. Yeah, there we go. Okay, right. If the rope was not modelled as being light, state how this would affect the tension along the rope, explaining your answer. Right. If the rope wasn't modelled as being light, it would have a weight, yeah? Depending on where the weight is, if it's a uniform rope, the weight would be acting at the middle, yeah? Now, the tension's not going to be the same throughout the rope, therefore, is it? Because the tension's going to grow as you get closer to the centre of mass, yeah? So what we can say here is the tension will increase as you go up the rope towards the centre of mass. And yeah, the more obvious way of pointing that out is because it's supporting more rope. So the tension would be variable along the rope, which is actually what happens in real life. This is why these models are not perfect. Okay, last one. Let's do it. Question 11. So, okay, I think this is the last one. Please tell me this is the last one. Okay, so police questions. Very common. Once again, you'll find these in the old M1 papers. There's loads of them. There really is to practice, so do make sure you practice them. Now, the first part of this is really nice because the plane is smooth, yeah? And in police questions, you always set up an equation of motion for A and an equation of motion for B, by which I mean Newton's second law for A and Newton's second law for B. Okay, we've got 3G here. Notice, even though I could possibly do this in my head, I don't try because I know I'll make a mistake, yeah? You always draw the diagram. There's no friction on this one, yeah, because the plane is smooth. Okay, so if I want to find the value of t, I'm just going to do 3g minus t is 3a, because I know the system's moving in that direction, yeah? Now you might say, well, how do you know the system's moving in that direction? I think they might tell you somewhere, but also 3g is larger than 3g sine theta, so it must be moving in that direction, because you can ignore the internal tensions here and just think, well, that force at this end is stronger than that force, which is putting it back down here. And so stronger force minus weaker force is mass 3 times acceleration. Now do it different for the other one, because t is going to be the stronger force this time, and 3g sine theta is going to be the weaker force, and that's going to be equal to 3a as well. Now they wanted us to find t, so we might as well eliminate a here, as we know this equals 3a and that equals 3a. Normally I'd add these two together to find the acceleration, because often they ask for that, but here this time I'm just going to say, well, that means that 3g minus t is going to be equal to t minus 3g times 2/7, because they told me that was 2/7, and so I can add the t to get 2t, if I put that on that side, and then do 3g plus 6g over 7. And so t is going to be equal to, well, that's 27g over 7, 27g over 14, I think. Okay, let me just check my answer there. Looks right though to me. I think so. 27g over 7. Yeah, let me just check. They reckon 18.9. Let's try. 27 times by... They don't mind if you leave the answer exact, by the way, if you're wondering if they mind if you leave the answer exact. They do not. But sometimes it's nice to write both, isn't it? Just in case you missed the word exact in the question, I think you've kind of covered yourself if you write it both ways, because if they did say give the answer exact and you've given it like that and then like that, I'd hope that they'd be reasonable enough to give you the full marks. Okay, that's the value of t. Right, part B is the tough bit. If I remember rightly, because somebody did ask me this the other day and I went through the question, it involves repeated applications of SUVAT, and that is confusing. And it's because of this idea of instantaneous rest, yeah? Basically, the particle's gone up, it's this one, it's gone up the plane, and then it's skidded up to the top, and it's just started to come back down again because the string goes slack. So after the string's slack and this one's actually on the ground, yeah, this skids up a little bit and then comes back down. And instantaneous rest means the top of its journey, its peak. It's the same if you've got something and you're just throwing it up and down in the air. Instantaneous rest is the peak of the flight, if you like. Okay, so let's do this. Now, what do we know? First things first with these, we want to find the speed just when the first object hits the floor. We want to find the speed then. Now, it's been released from rest, so u is 0. We already know from the earlier bit what t is, and we could find the acceleration of the system. Yeah, we could have done it if we use these two equations here. Let's just quickly find the acceleration. If you add them together, you eliminate the t's and you get 3g minus 3g sine theta equals 6a. In other words, 3g minus, now that's 2/7, wasn't it? So this is going to be 6g over 7 equals 6a. And so you've got, what is that, 21g over 7 minus 6g over 7. That's 15g over 7, but that's 15g over 42 is a. I think you can even cancel that down to 5g over 14, and that's your acceleration. So run that through in the first part to quickly get the acceleration of the system. We're going to be doing SUVAT a lot more here. Now, did they tell us 0.8 meters above the ground? So S is 0.8, and we can find what we really want to do here is we really want to find the speed just before this hits the ground and just before the string goes slack. So v squared is u squared plus 2as, and so that gives me v squared is 0 squared. This is 4/5, and so if you times it by that, you're going to have 4g over 14, which is 2g over 7. And so v is the square root of 2g over 7. Yeah, tell the examiner what you've just worked out. Speed just as b hits floor. Yeah. So now I'm going to use that as my speed for this one just before the string goes slack. Thus, you've got u equals root 2g over 7. You've got now we've got other things to work out here. Yeah, we know the new speed of this one. What I really need to work out now, I know the v is going to be 0 when it reaches its peak height, but I really need the acceleration, or in other words the deceleration when the string is slack. And I can do that because I can actually, before I do another SUVAT, I can use Newton's second law. Newton's second law, draw the diagram out again. I've got no friction, but I have got weight. Yeah, I can't remember what the mass of the object is. 3g. Yeah, you've only got the force of 3g sine theta acting down the slope. You've got no force pulling it up the slope. So we can say minus 3g sine theta, and this is definitely a bit of a question which I think students find the toughest. It is quite tough, this. That force down the slope is going to be equal to its mass 3 times by acceleration a. That's giving us the deceleration. That's why I've called it negative, because now I can see that the deceleration is minus g times 2/7, minus 2g over 7. That's our deceleration. So what have we got? We've got u is root 2g over 7. Yeah, the initial speed just before the string goes slack is that. The acceleration is minus 2g over 7. The distance is what we're looking for, and the velocity is going to be 0 because it's going to be right when it gets to instantaneous rest. Yeah, so it's literally, we're just trying to work out the speed of it just before it turns back round on its journey up and down the plane. Okay, and S is question mark. So we've got 0 equals u squared 2g over 7 minus, well, plus negative, but minus 2 times by 2g over 7 times by S. This gives us quite a nice answer, I think, because we're going to have 4g over 7 times S equals 2g over 7. And so by the look at that, S equals a half. Let me just quickly check that. I think I might have made a mistake here. Let's just quickly have a look. 2 times A times by S. Did I make my mistake earlier? G sine theta, no, that's good. 2 times by A times by S, 4g over 7. Because that looks like definitely a half to me. Did I just mess up something over here? A is 5g over 14 times by 4/5. Going to be 4g of 2g of 7. That looks good. Whenever I do things in my head, it's inviting trouble. Just have a look carefully at this. V squared 0 equals u squared minus plus 2 times by a times by s. That's good. 2g over 7. That's good. I think it seems to be saying it's over here. Let me just check this then. A is 3.5. Is 5g over 7 3.5? Let's look. 5 times 9.8 divided by 7. I think I've made a mistake here. I think it's up here when I've worked this out very casually. So if you're screaming at the screen, no doubt you were probably right. Let me have a look at this. Let me just quickly check my working here. 6g over 7, 3g minus 6g over 7, 21g over 7 minus 6g over 7 is 15g over 7. That looks all right to me. Have I just written down my equation incorrectly then? Let's just have a look. What a mess. I'm just doing it on my calculator now to check that my arithmetic is right. Rather embarrassing. Right, 21 minus 6 divided by 7. There is something there. 3g times by 2g over 7. Oh, 3g times by 2/7 is 6g over 7. That looks fine. Yeah, let me just check that. 5 times 9.8. Oh. Divided by 14. Oh, have I just... I think what it is, I've got 5g over 14 there. 5g over 14 here. And then have I used 5g... Yeah, because 5g over 14 is correct. This is correct. This is correct. Okay, let's just check that bit then. 2 times 5g over 14 times by 4/5. I think I just missed out the 2 here. I think that's what it was. 2 times by 5g over 14 times by 4/5. They cancel. That's 2g of 4g over 7. There we go. Yeah. So this is a danger of rushing things. Yeah. Don't rush. Don't be me. Don't be me. Okay, so we get root 4g over 7 here, and that's why I am out by a factor of 2. So there we go. It's a good to show you really, I guess, that you've got to check your answers. Don't assume that your calculations in your head are right. Quite often, actually, when I'm marking, I see this as well, because people, think, yeah, I don't need to calculate, just like I did, and you then make mistakes. And so S equals 1, yeah? And so the final answer, the distance it travels, is 1.8, because you have to add on the 0.8 meters. I hope that makes sense. Yeah, apologies for my blunder there, where I basically failed to calculate V correctly there. Okay, I hope that makes sense. I hope the question makes sense, and I hope that was useful. Best of luck in your revision, and come and find us in the maths department if you're stuck. Bye bye.